So what I'd like to do is I'm the IC representative to hardware management for OCP. And so we share this project with the server project. It started in the server project, and we brought it into hardware management as part of Run BMC, which was also a modular firmware connector. So I'm actually a student. The actual presenters are doing a complete video, and they're just using my to broadcast.
Welcome to the 2021 OCP Summit and the DC-SCM 2.0 specification update session. I'm Chen Wang, one of the project leads for the hardware management module working on the DC-SCM 2.0 effort. Together with Tim, we will provide an update on the DC-SCM 2.0 specification progress. The DC-SCM 2.0 is a collaboration effort among many companies. The motivation for the 2.0 initiative is to extend the scalability and longevity of the DC-SCM form factor and the DC-SCI interface. I would like to take this time to recognize the hard work from all the participants and public reviewers. We appreciate your expertise and involvement in making this project a success. Those who have signed the CLAs as of October 2021 are listed here on the slide. There are also a few more in the CLA signing process. Diving into the technical details, these are the high-level changes made in the DC-SCM 2.0 comparing to the 1.0 spec. To achieve universality, we are adopting the plug-and-code model for 2.0. This means that the DC-SCM CPLD and the HPM CPLD will need to meet a minimum set of requirements on installation and be reprogrammed before fully functional. Same for the VMC, it is also needs to be reprogrammed to match the platform architecture that it resides on. We included additional potential manageability interfaces such as PCIe, USB, and I3C for future use. We have a detailed interface comparison table in a later slide, so we'll touch on the details there. We refine the power states and discovery sequence for better universal electrical compatibility, as it is one of our goals in 2.0. Without breaking electrical compatibility, we have a dual node alternative pin definition overlaid on top of the single node pinout to support a dual node architecture. We also introduced a high-speed serial interface, LTPI. It stands for LVDS tunneling protocol interface for pin reduction, since we need much more pin on the connector, signal definitions on the connector. And last but not least, we have several mechanical adjustments in the works, including a foolproof mechanism to differentiate between the DC-SCM 2.0 and 1.0. This is a high-level example diagram. It's not too different from 1.0 with typical manageability components. Security features remain optional, such as the root of trust and TPM. This diagram shows the added PCIe, USB 3.1 I3C, and the LTPI interface. This is a dual node example diagram where we have 2 times the eSPI, QSPI, and PCIe USB interfaces, where the slower interfaces are tunneled over LTPI, such as I2C, UART. They're more tunneled interface in the dual node architecture than the single node. In this architecture, it is recommended for the TPM to reside on the HPM as compared to single node, where we still recommend to have the TPM on the SCM. And yes, this is assuming that the BMC can manage 2 independent nodes. In this slide, this is a brief overview of the LTPI interface compared with mainly the SGPO interface in 1.0. Casper and E from Intel are the main contributors and authors for this chapter of the spec. This diagram shows a comparison between 1.0 and 2.0. 1.0 defines the 2x the SGPIO, which uses 9 pins, and many other dedicated GPIOs on the pin definition. With the LTPI interface, higher speed differential signal pair, we only use 8 pins, and we can serialize many more GPIOs and remote peripherals, such as I2C, UART, and OEM-specific protocols. So please see the on-demand video on LTPI workshop for more details, and also we have this documented in detail in the spec as a chapter of the DC-SCM 2.0 spec. So from the mechanical perspective, Glenn from Intel is the author for the 2.0 mechanical chapter. He is working on refinements for the 2.0 models and drawings. And also, I would like to now acknowledge Andy from Lenovo for many great ideas and proposals he has provided in the mechanical workstream. So at a high level, the dimensions of the horizontal form factor remain the same as 1.0. The vertical form factor details are removed from the 2.0 spec due to lack of involvement there. A few modifications shown in the drawings on the right. The shifted connector gold fingers, added optional handles for inserting and removal of the card, added a pair of notches for internal locking. So overall, we more genericized some of the areas for flexibility and clarified the model for and requirements for a more universal compatibility. So Tim will go through the rest of the slides from here, and thank you so much for joining this session. Enjoy the conference.
So the DC-SCM's the work group needed some additionally more rigid rules on required versus optional key electrical sequencing and boot steps, more generic in ways with options for a more conservative discovery sequence. It was important to establish guarantees for electrical safety through a controlled way to halt or to move forward in the boot progression. So we also were able to come up with common nomenclatures for names of each of the power states, as well as the ability to source the minimum power from the DC-SCM back into the HBM to power a FRU, and that's assists the discovery mechanism, as well as a optional crypto authentication binding integrated circuit. So this helps ensure an authentic DC-SCM is coupled to the HBM before allowing the host domain to progress to code execution, which is very important in the fact that it is a decoupled platform root of trust away from the core host domain. So this was really key to those threat vectors of it, the DC-SCM and the center of truth of security being on a replaceable board. We also were able to narrow the total power. This helped with the total power range to something more compatible with other common standards, and it also was able to increase the overall power envelope available to the DC-SCM card. As trends in the industry are moving toward, in certain chipsets, a external discrete RTC, which is more efficient from a power perspective, where we're able to increase the amount of power consumption of battery drain that the DC-SCM could pull by a little bit. And we're also able to refine the physical handshakes and gave a lot of examples of typical virtual handshakes as you're going through the discovery sequence up through what would be an AC off situation to system standby to a system full on state. From the interface definition perspective, we were able to come up with common naming conventions, which really helps understanding as someone's reviewing or creating hardware designs off of this specification of the fabric, the source, the destination of any given signal, as well as the instance number, and in a multi-node situation, which node those signals are associated with. And this also helps us be able to cross-reference the signals with the text document as well. So the group went through a best fit exercise of all the different pins through the SAI interface with possible multifunction pin overlays, voltages, compatibilities, right-size the different bus counts for the types of targeted applications that we think will help the DC-SCM be able to progress and have much more longevity and applicability across different platform types. It's important to note here that there have been at least 4 prior industry standardization efforts that largely failed due to the lack of agreements or the ability to cost-effectively converge on what are historically eclectic platform-specific systems management needs. And so that's where a bulk of the refinements that went into the DC-SCM 2.0 spec have helped try to create future-looking but still right-sized and appropriately designed pin overlays for the maximum functionality for the maximum number of identified use cases. So it's important to note here that the DC-SCM's primary value proposition is more around the modularity tenets, including efficient development, leveraged validation, and customized systems management and security practices for different platforms and OEMs. However, the pin assignments and the typical use diagrams that are included in the 2.0 specification attempt to optimize costs where possible. In this endeavor, we were also able to define the minimum power state for each of the pins that can tolerate bias within the different power states. This is important to ensure that you have maximum electrical compatibility and minimize the necessary cross-power domain types of isolation logic that would have been needed otherwise. So that is a very important improvement in the 2.0. We also, in the spec, just in the construction of it, were agreed to split out the pin list and the pinout from the Word document itself to be a standalone spreadsheet. And this helps consolidate and minimize duplicated information in multiple areas. And that seems to be, in the reviews so far, going pretty well. From the specific interface perspective, this chart shows the major types of changes from the bus type. And the SGPIO, the single-ended serial GPIO, was removed and in place of the LVDS high-speed differential interface that there's a that had been previously discussed in this forum, as well as another forum within this OCP Summit dedicated specifically to the details there. We were able to maintain the maximum use of I2C at a 3.3 volt level for typical use cases, as well as start this migration toward 1.8 volt as new chip technologies are coming along, that as well as the presumed crossover for I3C picking up steam in certain types of applications. So there was a balance there to be able to support I2C or I3C at the 1.8 volt, and that voltage was chosen for the maximum bus length type situations. We also know that there are specific applications where lower voltage is needed, so there are a couple buses that are very specific to lower voltage I3C compatibility, as well as dedicated multiple buses for the open power FSI interface that is native in certain BMCs and is a very high speed 2-pin interface. The PCIe topology offered quite a few enhancements, both southbound toward the SCM as well as northbound, inclusive of the BMC's root complex, expanding peripherals into the HPM, and high-speed management of different types of HPMs, such as FPGAs and other types of targets. The USB topologies have included numerous options on both the direction of the buses and whether they're in the host or management domain. And so managed USB is a very powerful, flexible, high-speed management interface for remote peripheral expansion and interface into different types of forthcoming peripheral expansion needs. So the enhancements include evolutions such as the general HPM SoCs decoupling their host USB controllers. And further, USB 3.1 options are also included for scenarios where such as where an SCM located host domain controller may wrap around to the host USB devices on the HPM itself, or preparing for the presumptive evolution of a managed USB buses to be moving toward a 3.1 super speed interface. There were numerous SPI bus enhancements, which included right leveling the voltages, evolving the different TPM bus needs, which are changing in different chipsets, and an SCM-sourced interface for various interesting potential use cases, such as a higher speed HPM FPGA immutable attestation interface, as well as for the FPGA update and recovery. NCSI remains overloaded with other functions, of course, and a second NCSI interface was added for redundancy or for multi-node support as well. And so much debate occurred on potential USB displacing RMI-based transport for the NCSI protocol, but we understand that shorter term, there's still some applications that can use that. As we discussed earlier, there's a power pin for the FRU related to the discovery sequence. And then certain signals that were fixed function, like virtual reseat and firmware recovery, were removed as discrete pins, as alternate methods exist for the same functionality without requiring dedicated pins. So future exploration topics include a new or an optional expansion connector for more pins where needed. This effort really went toward reusing the industry standard 4C+. There were other options considered, but it's still fixed at the 168-pin interface as the 1.0. But it is recognized that the usefulness of the DC-SCM 2.0 or DC-SCM could be enhanced quite a bit if more pins were available in the future via different types of expansion connectors or whatnot. There's discussion of creating a compliance test vehicle as more interoperability is desired between different DC-SCMs and HPM complexes. And then we want to continually keep tabs on the evolving types of interfaces. Like I said earlier, the right sizing and the future proofing, but still being able to absolutely optimize the pin usages was a big endeavor that we want to keep maintaining to make sure that we can evolve as different use cases and models and bus evolutions occur. So the call to action is that there is a public wiki site that includes the specification as well as the pin list, and there's a mailing list. And we would like to call out for the community to continue to add what they feel are missing or a wish list of types of things that you wish a DC-SCM could do, or the DC-SCI, whether it be mechanical, thermal, electrical, logical domains. Anything and everything is asked for so that we can consider and as a work group continue to evolve and make this spec better. There are specific contributions targeted for 2022. And there's also during this OCP conference an LTPI demo specifically to give you a deeper dive into that new feature-rich interface. Thank you.
They won't hear you, but you can clap. So I can ask for questions. I can answer most questions about it. If not, in about a couple of minutes, we're going to have a deep dive on the LTPI interface, which they have mentioned here. It's a 5-minute. It's basically a teaser to go onto the virtual site and look for all the details of what is already there. So.
I have a question here.
Yes.
So for DC-SCM 2.0 standard, what's the timeline? Currently, it's still not finalized, right?
No, it's not finalized, but the drafts are being posted on the wiki, so yeah. I don't remember what revision is currently posted. But as he mentioned on his call to action slide, the target is 2022.
2022 to finalize.
There will be contributed, the entire final spec will be contributed to the IC for ballot, and then it will become official.
Do you expect any vendors build based on the 2.0 standard before that?
They do so at their own risk.
Okay.
So, I mean, there are candidates of who's working on it. They or release something at their own risk.
Do you expect this becomes like a OCP NIC kind of, you can buy off the shelf from like ASP or any vendors and plug into any other compatible server to work, or what's the?
That is the vision.
That's the vision.
Is that right? Is that the process of producing DC-SCM 2.0 products? It's actually one of the requirements for the IC to accept the specification, is that products are right behind it within 120 days. The demo over at the Experience Center is actually a Lattice ASIC, which is the one of the components for the LTPI tunneling interface. And basically, yeah, it's a standard. It should work with anyone else's module.
Sorry, it's basically processor agnostic, no matter which CPU.
Yes, it's an interface. It's an interface standard, which means the implementation on either side is agnostic to it.
Okay. How about the ROT module? Is there any change on the 2.0 for the ROT feature?
For which module?
The root of trust features on the DC-SCM.
I don't believe so. I don't believe we've touched the root of trust on either the SCM 1.0 or 2.0. Right? Please.
Thank you.
These questions, high-level answers. The choice of root of trust on DC-SCM is not specified. So most of the work is to make sure the interface works between DC-SCM and HPM. So people have the freedom of putting whatever BMC they want or whatever root of trust they want. That's at this level. But you guys might say, hey, that's not a complete system. So as you asked, who's going to build it? That's why we have a bigger discussion nowadays about a data center ready modular hardware system on top of it. So that is part of the discussion for next year. So the systems will be complete.
Are we rolling to the next presentation?
Sorry, I have one more question.
Oh, sure.
For the DC-SCM, I see you only show the one form factor actually. Are you going to have the vertical?
If you need other form factors, please join and contribute and
ask.
And ask and do.
It was in the 1.0.
For the 1.0, there were enough requests for different form factors, and actually because it was the first time around, we were thinking about more. Again, the form factor itself is not part of the spec. It is just as an example of what can be done. Interface is very important to be fixed. Form factor, depending on technology or techniques that you want, could be cabled in, could be plugged in from vertically, or can be plugged in horizontally. That can still be done with DC-SCM 2.0 spec. It is just you don't have any guidance on how to do it. You can do it as long as the interface is the same as DC-SCI, the interface part. It will still work. The end result at the end is for software to run flawlessly. Specific module form factor will evolve. Hopefully there will not be too many of them around, maybe one or two, for good reasons.
But you are open for.
Oh, of course, the spec is open. That's your spec.
Cool.
Archana said, we are OCP. All of us are OCP.
All right.
So you can blame yourself if it doesn't do what you want. Okay, so this is a short presentation on LDBS. This is the differential signaling that we tunnel the signals across on SCM 2.0. So both Casper and United and good. So a quick background, introduction to the interface, its key features, and a quick call to action. The background is that the modular, the reason for DC-SCM was to move manageability and the root address onto a modular platform. 1.0 and 2.0 both use the SFF connector, but it's limited to 128 pins. You have to stay within that. So in 1.0, we had two serial GPIOs, which took up 9 pins. There were additional pins that were also being used in order to, quote, kind of bifurcate that in order to support a partition system with 2 CPUs. You needed more pins. Some pins had to go. The was that currently, this is how it looked in one. So in 2.0, those pins were replaced with the TPI, which basically introduced voltage differential signaling, and then tunneled most of the through it. There's 4 differential links. So 6 PI pins, you actually 1 pin 6 pins, so you've kind of benefited. And so in addition, we tunnel more than just GPIOs. Live? Okay. Yeah. So in addition, we want to tunnel more than just GPIOs. Since we had we're tunneling a bunch of interfaces through. So this is a overview of what it looked like. So on the right-hand side is all the signals coming off the HPM. It gets tunneled through a FPGA. It goes across the connector. It gets tunneled basically, and all those feed into the BMC. So there's examples of those by Lattice, which is out on the Experience Center floor, if you want to take a look at it. And these are the key feature recaps. I think he went through in the last presentation pretty in-depthly on what was actually changed. So it was a low voltage signaling. They used AC coupling. As I demonstrated, the multiple interfaces were being tunneled through, not just GPIO. It has much higher bandwidth. So the latest implementation, FPGAs, it's 1600 megabits. It's scalable, it's flexible, and as someone had a concern, at least this portion of it is interoperable, and the rest of DC SCM 2.0 will be similarly interoperable with different vendors appearing on different motherboards. And there was supposed to be a set of 3 demos actually in the Experience Center from Intel. They're all done in virtual form on demand. So if you go to Experience Center, the virtual Experience Center for the summit, you can see all the demos. The only live demo we have is the one from Lattice. Okay, with that, are there any questions? Then I'm done. Thank you.